Dark matter is an elusive and mysterious substance that does not emit, reflect, or absorb light, making it invisible to modern telescopes. Although it is invisible, it exerts a gravitational pull that affects the motion of galaxies and galaxy clusters. It is estimated that about 85% of the total mass of the universe is dark matter, suggesting that the ordinary matter we observe, from stars to planets, makes up only a tiny fraction of the pillar of the universe. The discovery of dark matter dates back to the early 20th century. In the 1930s, Swiss astronomer Fritz Zwicky observed a cluster of galaxies in the form of a coma and discovered that the galaxies were moving too fast to be held together by visible matter alone. He coined the term Dunkelmarie to describe this invisible mass, which means dark matter and dark matter. Vera Rubin obtained even more convincing evidence in the 1970s when she studied the rotation curves of spiral galaxies. Rubin found that stars on the outer edges of galaxies rotate as fast as stars in the center, a phenomenon that cannot be explained by the presence of visible matter alone. It suggests that there is a significant amount of invisible mass exerting a gravitational influence. Modern technological advances continue to shed light on dark matter, albeit indirectly. Observatories such as the Hubble NDAMP. Space Telescope have provided insight into it through gravitational lensing, where light from distant galaxies is deflected by the massive invisible objects between them and us. Although scientists have not yet been able to directly detect dark matter particles, numerous experiments are currently underway to determine what dark matter is actually made of, with hypotheses ranging from WIMPs, weakly interacting massive particles, to axions. Understanding dark matter remains one of the most pressing and tantalizing challenges in cosmology today, which promises to redefine our understanding of the structure and evolution of the universe. Dark matter plays a key role in shaping the structure of the universe on both large and local scales. The influence of dark matter is ubiquitous and shapes the cosmos, from the formation of galaxies to the behavior of entire galaxy clusters. Because of its invisible nature, the presence of dark matter is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. In the early universe, shortly after the Big Bang, dark matter acted as a cosmic framework around which ordinary matter could gather. This matter contributed to the formation of the first galaxies and galaxy clusters. Without the gravitational pull of dark matter, the gas needed to form stars, and galaxies would not be compressed as efficiently. The so-called cosmic web, a vast network of filaments composed mostly of dark matter that connects galaxies and clusters, demonstrates how dark matter organizes matter on the largest scales. These strands of dark matter attracted ordinary matter, guiding the formation and distribution of galaxies and intergalactic gas along their length. On smaller scales, dark matter also influences the internal dynamics of galaxies. Observations of the rotation curves of spiral galaxies, where stars at the outer edges rotate faster than the apparent mass alone predicts, indicate the presence of a vast amount of invisible mass, dark matter, extending far beyond the visible edges of these galaxies. This invisible halo of dark matter stabilizes galaxies, preventing them from being torn apart by their rapid rotation. Consequently, dark matter is fundamental to the formation, structure, and ultimate fate of the universe. Understanding its properties and interactions remains one of the most exciting challenges of cosmology. As we learn more about dark matter, we will inevitably gain a deeper understanding of the evolution of cosmic structures and the very structure of the universe, as well as open up new areas of physics beyond our current knowledge. The detection of dark matter, given its elusive nature, is one of the most intriguing challenges in modern science. Because dark matter does not emit, absorb, or reflect light, scientists rely on indirect methods to determine its presence and properties. One of the main ways to detect it is to observe its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Gravitational lensing is a powerful tool for detecting dark matter. When light from distant galaxies passes through a cluster of galaxies, the cluster's enormous gravitational field, which includes a significant dark matter component, bends the light, distorting and magnifying the image of background galaxies. By mapping these distortions, astronomers can draw conclusions about the distribution and amount of dark matter in a cluster. Lensing often reveals more mass than can be seen, suggesting the presence of dark matter. Another method involves the rotation curves of galaxies. When astronomers like Vera Rubin studied the rotation rate of stars in spiral galaxies, they found that stars on the outer edges of these galaxies rotate as fast as they do near the center, contradicting expectations based solely on observed matter. This uniform rotation rate suggests the existence of a halo of dark matter enveloping the galaxies and providing the extra gravitational pull needed to keep the stars moving so quickly. On a more experimental front, scientists are using underground detectors to capture potential dark matter particles. Direct detection experiments, such as those using cryogenic detectors or liquid xenon targets in facilities such as the Large Underground Xenon Experiment, LOX, aim to observe rare interactions between dark matter particles and ordinary matter. When a dark matter particle collides with a nucleus in a detector, it can release a minuscule amount of energy in the form of light or heat that sophisticated instruments can detect. Finally, particle gas pedals such as CERN's Large Hadron Collider, LHC, investigate the existence of dark matter by colliding protons at high energies. Collisions can create dark matter particles. Whether or not they can be detected can be judged by the lack of energy and momentum in the particle tracks obtained. Although dark matter has not been directly observed, these techniques provide strong evidence for its existence and continue to elucidate its possible properties. The quest to directly detect dark matter remains an exciting area of the ever-evolving field of cosmology that promises to reveal new aspects of our understanding of the universe. The composition of dark matter remains one of cosmology's most tantalizing mysteries, and several leading theories have emerged to explain its elusive nature. According to one of the most common theories, dark matter consists of weak or weakly interacting massive particles. It is believed that these hypothetical particles were produced in large quantities in the early universe and could explain the vast amount of invisible mass based on their weak interactions with ordinary matter and electromagnetic radiation. WIMPs are attractive because they fit well within the standard model of particle physics and its extensions, such as supersymmetry, which predicts the existence of such particles. Another compelling candidate is the axion, a particle first proposed in the late 1970s as a solution to the strong CP problem in quantum chromodynamics. Axions, if they existed, would be very light and would have very little interaction with ordinary matter, making them difficult to detect. These may have appeared in the early universe in sufficient quantities to explain dark matter, and they are being actively searched for in experiments such as the Axion Dark Matter Experiment, ADMX, and other initiatives. Sterile neutrinos are another interesting possibility. Unlike known active neutrinos, which interact via the weak nuclear interaction, sterile neutrinos interact only via gravity. Their mass could help explain the observed properties of dark matter and play a role in the formation of large-scale structures in the universe. The discovery of sterile neutrinos would have profound implications for our understanding of dark matter and elementary particle physics. There are also more exotic theories, such as the idea that dark matter is made up of primordial black holes. These black holes may have formed in the early stages of the universe due to strong density fluctuations. Although they are difficult to detect, they may contribute to gravitational effects caused by dark matter. In addition, some theories suggest that dark matter may not be composed of particles, but rather a variation of the known laws of gravity. One such theory is modified Newtonian dynamics, MOND, which proposes to modify Newton's laws on cosmic scales to account for the missing mass in the universe. However, this idea is less popular because it cannot explain observations on different scales as fully as particle-based theories of dark matter. Each of these theories has been the subject of rigorous experimental and observational study. Progress in this field not only promises to solve the mystery of dark matter, but may also reveal new physics that could overturn our view of the universe. Dark energy and dark matter are two of the most enigmatic components of our universe, each playing a separate and key role in its evolution, yet radically different in their nature and effects. Together, they make up about 95% of the universe, with dark energy making up about 70% and dark matter about 25%. Dark matter is a form of invisible mass that exerts a gravitational influence, contributing to the formation and clustering of galaxies and galaxy clusters. The gravitational influence of galaxies helps them maintain their integrity, providing the extra mass needed to explain the observed rotational velocities of stars on the outskirts of these galaxies. Although dark matter does not interact with electromagnetic forces, making it invisible to light, it is still compressed by gravity, guiding the formation of large-scale cosmic structures in the universe. Dark energy, on the other hand, is a mysterious force that appears to drive the accelerated expansion of the universe. Dark energy, first discovered in the late 1990s through observations of distant type Ia supernovae, acts as a kind of anti-gravity, counteracting the attractive force of gravity on cosmic scales. Unlike dark matter that clusters together, dark energy is thought to be uniformly distributed in space, affecting the geometry of the universe and its rate of expansion. The nature of dark energy remains one of the central mysteries of modern cosmology, and it is often modeled through the cosmological constant, a term introduced by Einstein, or through more dynamical fields such as quintessence. The influence of dark energy is most obvious when considering the large-scale structure of the universe and the rate of its accelerated expansion. It stretches space itself, affecting the rate at which galaxies move away from each other. This accelerating expansion has profound implications for the future of the universe, suggesting that it could continue to expand forever, leading to a cold, dark, and increasingly diffuse cosmos. While dark matter binds galaxies and clusters together through its gravitational attraction, dark energy pushes them apart, dominating the dynamic evolution of the universe on the largest scales. Understanding both phenomena is crucial to gaining a complete understanding of the origin, structure, and ultimate fate of the universe. Researchers continue to use a range of observational strategies, including measurements of the cosmic microwave background, large-scale galaxy surveys, and gravitational lensing studies, to explore these dark components and unravel their mysteries. Dark energy has a profound effect on the expansion of the universe, acting as a mysterious force that accelerates that expansion. This discovery, which refutes previous ideas about slowing cosmic expansion, came from observations of far-infrared supernovae in the late 1990s. These supernovae, considered standard candles because of their constant intrinsic brightness, have allowed astronomers to measure distances to distant galaxies. They found that galaxies are not just moving away from us, but are accelerating in their distance, meaning that some unknown force is pushing them apart at an increasing rate. The role of dark energy in the accelerated expansion of the universe can be understood through its effect on space-time itself. Unlike ordinary and dark matter, which bind together and exert a gravitational attraction, dark energy is thought to have a repulsive effect. It is uniformly distributed throughout the universe, resulting in a constant energy density even as space expands. This characteristic can be modeled as the cosmological constant, denoted by the Greek letter L in the field equations of Einstein's general theory of relativity, denoting the form of vacuum energy that permeates all of space. Since dark energy dominates the energy composition of the universe, its repulsive force dominates the gravitational pull of matter. As a result, the fabric of space-time is stretched, accelerating the rate of expansion of the universe. Modern measurements show that dark energy makes up about 70% of the total energy content of the universe, resulting in an accelerated expansion that at first seemed counterintuitive to many cosmologists. The consequences of this accelerated expansion are profound. As time goes on, galaxies will move farther apart, and the observable universe will become more and more isolated. This phenomenon could lead to a big freeze scenario where galaxies go over the horizon and become unobservable. Stars burn up, and the universe cools to the point where thermodynamic activity ceases. Another intriguing possibility is the Big Rip, an event in the distant future in which the influence of dark energy becomes so strong that it eventually tears galaxies, stars, and even atomic structures apart. Research is now underway to better understand dark energy, using techniques such as studying the cosmic microwave background radiation, analyzing large-scale surveys of galaxies, and observing gravitational lensing effects. By understanding the nature of dark energy, scientists hope to uncover deeper truths about the fundamental forces shaping our cosmos, and perhaps open up new areas of physics that lie beyond our current understanding. The strongest evidence for the existence of dark energy comes from a variety of astronomical observations and measurements that consistently point to an accelerated expansion of the universe. Taken together, all this evidence creates a coherent picture of dark energy as the dominant force in the cosmos. Some of the first and most compelling evidence came from the study of distant IA supernovae. In the late 1990s, two independent research groups, the Supernova Cosmology Project and the High Z Supernova Search Team, observed these supernovae as standard candles due to their uniform intrinsic brightness. By measuring apparent brightness and redshift, scientists have found that distant supernovae are systematically darker than expected. This decline suggests that the rate of expansion of the universe has accelerated over the past billions of years, implying the existence of a repulsive force called dark energy that opposes gravity. Another important piece of evidence concerns the cosmic microwave background, relic radiation, and Big Bang remnants. The Wilkinson Microwave Anisotropy Probe, WMEP, and the Planck satellite have measured the relic emission with unprecedented precision. The results show small fluctuations in temperature that provide a better understanding of the early universe. By analyzing these fluctuations, scientists can determine the shape of the universe and its overall energy content. Measurements of relic radiation show that the universe is flat, implying a certain overall energy density. However, visible matter, dark matter, and radiation together account for only about 30% of this density, suggesting that the remaining 70% must come from dark energy. Large-scale studies of galaxy structure provide additional support. Projects such as the Sloan Digital Sky Survey, SDSS, map the distribution of galaxies in the universe. These studies help trace the large-scale structure of the universe and the patterns of galaxy clusters. Observations show that galaxies are not only moving away from each other, but also accelerating. This acceleration is consistent with the presence of dark energy. Additional confirmation is provided by the phenomenon of baryonic acoustic oscillations, BAO. In the early universe, pressure waves propagated through hot plasma, leaving marks on the distribution of galaxies. These marks, or sonic peaks, serve as cosmic benchmarks. By measuring the distance between these peaks in the distribution of galaxies, astronomers can trace the expansion history of the universe. BAO measurements are consistent with an accelerating universe driven by dark energy. Finally, gravitational lensing, in which light from distant objects is deflected by large structures in the foreground, also provides evidence. By studying how galaxies and galaxy clusters refract light from background sources, scientists can infer the distribution of dark matter and dark energy. The results support a model of the universe dominated by dark energy, which affects the overall mass-energy balance and expansion rate. Together, these diverse and converging lines of evidence provide compelling evidence for the existence of dark energy, profoundly changing our understanding of cosmology and the evolution of the universe. The potential interaction between dark matter and dark energy is a topic that raises some of the deepest questions about the composition and evolution of the universe. Although both of these phenomena are of great importance to our understanding of cosmology, they have fundamentally different properties and roles. Dark matter, with its gravitational coupling, serves as the basis of cosmic structures, while dark energy drives the accelerated expansion of the universe. In the current cosmological model, the standard cold dark matter lambda model, LCDM, dark matter and dark energy, are generally considered as separate and non-interacting components. Dark matter contributes to the formation and stability of galaxies and clusters through its gravitational attraction, while dark energy, often modeled as the cosmological constant lambda, exerts a uniform repulsive effect on all of space, causing cosmic acceleration. However, some theoretical models suggest potential interactions between dark matter and dark energy. These interactions can alter the behavior of both components over cosmic time. One such model includes the notion of bound dark energy, where the density of dark energy changes with time, potentially interacting with dark matter in ways that alter its properties or distribution. For example, dark energy can decay into dark matter particles or vice versa, which affects the relative amount and distribution of these substances in the universe. Another interesting model is scalar field dark energy, in which dark energy is described by a dynamical scalar field rather than a constant quantity. In these models, the scalar field can interact with dark matter, affecting its clustering behavior and the overall dynamics of cosmic structures. This interaction can lead to observable features in the large-scale structure of the universe, such as changes in galaxy clustering or variations in the cosmic microwave background radiation. Experimental and observational work has not yet provided definitive evidence of such interactions. However, precise measurements of the cosmic microwave background, galaxy clustering, baryonic acoustic oscillations, and the distribution of large-scale structures continue to break new ground. For example, deviations from expected behavior in these observations may hint at interactions between dark matter and dark energy. Another area of research is high-energy particle physics experiments, which may reveal new particles or forces that could mediate the interaction between dark matter and dark energy. Experiments at facilities such as the Large Hadron Collider, LHC, and various dark matter detection experiments can provide indirect evidence of such interactions by revealing anomalies that cannot be explained by the existing model. Although the standard cosmological model currently treats dark matter and dark energy as independent, conceptual models and current research are exploring the possibility of their interaction. The discovery of any such interactions will greatly expand our understanding of these enigmatic components and could lead to revolutionary changes in our understanding of the fundamental forces of the universe and the underlying physics. Understanding the true nature of dark energy presents many challenges, both observational and theoretical, that scientists are striving to overcome. These challenges stem from the elusive properties of dark energy and the limitations of our current models and technologies. One of the main challenges is its detection and direct measurement. Unlike dark matter, which has a gravitational effect observed through its influence on galaxies and cosmic structures, the influence of dark energy is more subtle, manifested primarily in the accelerated expansion of the universe. This acceleration can be inferred from indirect observations such as redshifts of distant type Ia supernovae and patterns in the cosmic microwave background radiation. These methods, while reliable, do not directly measure dark energy, leaving its nature somewhat ambiguous. Adding to the difficulty is the fact that dark energy makes up about 70% of the energy density of the universe. Yet it remains uniformly distributed and does not stick together like ordinary or dark matter. This large-scale homogeneity makes it difficult to isolate distinct regions of space where the influence of dark energy can be individually studied, which complicates the design of experiments capable of investigating its properties. From a theoretical perspective, integrating dark energy into the existing framework of physics presents significant challenges. The most commonly used model, the cosmological constant lambda, represents dark energy as a constant energy density in a vacuum. This model, while consistent with current observations, suffers from the cosmological constant problem. This problem arises because the value of vacuum energy predicted by quantum mechanics is much higher than the observed value. Bridging this huge gap remains one of the deepest unsolved problems in theoretical physics. Other theories suggest that dark energy may be an entity-like dynamic field. This field varies in time and space, potentially interacting with other cosmic components, such as dark matter. However, these models introduce additional parameters and complexities, making them more difficult to test and validate against observations. Moreover, the theoretical tools needed to fully describe these dynamical fields often require extensions of the standard model of particle physics or modifications of the general theory of relativity, which creates a contradiction with established physical laws. The accuracy of cosmological measurements is also a challenge. Observing the universe with the precision needed to determine the properties of dark energy requires next-generation telescopes and instruments. Projects such as the Dark Energy Survey, DES, and the Euclid mission are designed to map large areas of the sky with high precision. But interpreting data from these large-scale surveys requires sophisticated statistical tools and deep theoretical understanding. Finally, reconciling dark energy with other fundamental forces and particles may require new physics that goes beyond existing paradigms. This may involve additional dimensions, modifications to Einstein's theory of gravity, such as FR gravity or scalar tensor theories, or entirely new kinds of particles and interactions. Developing and testing these ideas remains a challenge, requiring advances in both experimental techniques and theoretical foundations. The quest to understand dark energy is hampered by its indirect detection, the theoretical problems associated with its incorporation into established physics, the need for accurate cosmological measurements, and the potential need for new physics. Despite these obstacles, ongoing research promises to unravel this profound mystery, and each new observation and experiment brings us one step closer to understanding the true nature of dark energy. The impact of dark matter and dark energy goes far beyond their role in shaping the large-scale structures of the cosmos. These enigmatic components also significantly affect the ultimate fate of the universe. Understanding their interrelationships is essential for predicting how the universe will evolve and what it may eventually become. Dark matter, which makes up about 25% of the energy density of the universe, acts as the basic gravitational framework around which galaxies and galaxy clusters form. Its gravitational pull helps bind these cosmic structures together, counteracting the dispersive effect of the expansion of the universe. The presence of dark matter has allowed galaxies to cluster and persist for billions of years, forming the rich and diverse cosmic landscape we see today. In contrast, dark energy, which makes up about 70% of the energy density of the universe, acts as a repulsive force, that contributes to the accelerated expansion of the universe. Its influence was made clear by observations of distant type Ia supernovae in the late 1990s, which showed that the rate of expansion of the universe is not slowing down, but rather accelerating. This acceleration suggests that dark energy works against gravity, causing space itself to stretch at an ever-increasing rate. The balance between dark matter and dark energy will ultimately determine the fate of the universe. If dark energy continues to dominate, expansion will accelerate indefinitely, leading to what is often referred to as the Big Freeze or heat death. In such a scenario, galaxies would become increasingly distant from each other, stars would burn out, and the universe would become increasingly colder and darker as it expands. Over trillions of years, the remaining cosmic structures would become isolated and the residual heat would dissipate, leading to a state of thermodynamic equilibrium in which no meaningful physical processes would occur. An even more extreme option is the Big Bang scenario. If the repulsive force of dark energy becomes stronger over time, which contradicts the current cosmological constant model, the acceleration could increase to the point where it would tear galaxies, stars, planets, and eventually even atomic structures apart, splitting all matter in the universe. This would lead to a cataclysmic event that would result in space-time itself being torn apart. Conversely, if dark matter or a future understanding of dark energy reveals new physics that balances this acceleration, the universe could reach a steady state or even undergo a major crisis. In this scenario, expansion would eventually stop and reverse, leading to contraction, culminating in a singularity, possibly followed by a new Big Bang, according to some speculative models. In addition, theoretical models that study dynamic forms of dark energy, such as quintessence, offer more subtle possibilities. Such options include oscillating universes, in which periods of expansion and contraction follow each other cyclically, or scenarios in which dark energy diminishes over time, allowing gravitational forces to regain dominance. Current observations and cosmological data, such as cosmic microwave background radiation, large-scale structural studies, and supernovae measurements, strongly support a future dominated by dark energy and accelerating expansion. However, as research continues, our understanding of these dark components may change, which could lead to new discoveries and changes in our long-term predictions of the evolution of the universe. Although dark matter binds the universe together with its gravity, dark energy accelerates its expansion. The balance between these forces not only shapes the current structure of the universe, but also determines its future trajectory, offering diverse and profound possibilities from an ever-expanding universe to a cold and dark fate to more dramatic and speculative outcomes.